Hey everyone! In this video, we're going on a whirlwind tour of computing, starting from tiny microcontrollers and going all the way up to data centers. Along the way, we'll explore what microcontrollers are and where they're used, microcontroller boards, single board computers, SBCs, systems on a chip, modular designs, microprocessors, PCs and servers, graphics processing units, GPUs, the rise of Beowulf clusters and rack-mounted servers, and modern data centers and high-performance computers. Throughout this journey, we'll put special emphasis on the processing capacity of each system, so you can see how they compare. All right then, let's dive in. Let's start with microcontrollers. So what exactly are they? Think of a microcontroller as a tiny computer on a single chip designed to handle a few simple tasks really well. Unlike a laptop or smartphone, which can run all kinds of complex programs, a microcontroller is usually used to control a few specific functions. It combines a processor, memory, and input-output pins all in one package, making it compact and inexpensive. You'll find them everywhere, in washing machines, microwaves, cars, toys, and even medical devices. Basically, if a gadget can sense something, process it, and react, chances are a microcontroller is doing the work behind the scenes. They may not match the power of desktop processors, but because they're cheap, efficient, and reliable, microcontrollers are the hidden heroes running billions of devices around us every single day. Now that we know what microcontrollers are, let's take a step further and talk about microcontroller boards. A microcontroller on its own is just a tiny chip. Powerful, yes, but not exactly user-friendly. That's where development boards come in. A microcontroller board takes that chip and places it onto a small circuit board, along with all the extras you need to actually use it. Things like power regulation, input and output pins, USB connectors for programming, and sometimes built-in sensors or communication modules. These boards make it much easier for engineers, students, and hobbyists to experiment and build projects without worrying about wiring up every tiny component themselves. Some of the most popular examples are the Arduino boards, which kicked off the maker movement, or the ESP32, which adds Wi-Fi and Bluetooth right on the board. With these, you can go from an idea to a working prototype in no time. In short, microcontroller boards are the bridge that turns a bare chip into something anyone can use to build gadgets, automate tasks, or even prototype new products. Now, before we move on, it's worth talking about the processing limitations of microcontrollers. Most microcontrollers are designed for efficiency, not raw power. A typical low-end MCU might handle just a few million instructions per second. Even the faster ones usually top out in the hundreds of millions. That's plenty for tasks like reading sensors or controlling household appliances. But it's nowhere near the processing muscle you'd need for things like playing high-definition video or doing complex calculations. And that's exactly where single-board computers step in. They give you much more processing power while still staying compact. A high-end SBC can process up to a few billion instructions per second. So, for example, if you needed to do high-resolution video stream encoding or decoding, that would firmly be in the domain of SBCs. Next, let's take a look at a few everyday uses of microcontrollers. A good everyday example is inside remote controls. In older remotes, manufacturers often use custom-built chips, hardwired circuits that could only send a fixed set of signals. But in modern remotes, especially the ones with displays or extra features, you'll usually find a tiny microcontroller running the show. It reads your button presses, drives the screen, and sends the right infrared or Bluetooth signals. And because microcontrollers are relatively much cheaper, they are widely used in most remotes. So, the next time you grab a TV or air conditioner remote, chances are you're actually holding a little microcontroller in your hand. Another great example of microcontrollers at work is in air conditioners. At first glance, an AC looks like just an electromechanical appliance, but behind the scenes, a tiny chip is quietly running the show. The microcontroller's job is to read signals from the remote control and from sensors, things like temperature, humidity, or whether the unit is in cooling or fan mode. Based on those inputs, It decides when to switch the compressor on or off, how fast the fan should spin, and which mode the system should be in. Here's the surprising part. None of this needs a very powerful processor. A simple 8 or 16-bit microcontroller, like the classic 8051, or a PIC chip, is more than enough. They're cheap, efficient, and reliable, which is why they've been used in appliances for decades. But in modern air conditioners with smart features, Wi-Fi connectivity, smartphone apps, or even voice control, the requirements go up. For those, manufacturers use more advanced 32-bit microcontrollers or even small system-on-chip designs that can handle networking, encryption, and more complex software. So whether it's a basic unit or a smart connected one, the real brain of an AC is still a microcontroller, just scaled to match the features. Microcontrollers also play a huge role in industrial robots. On a production line, robot arms need to perform repetitive tasks with precision. Things like welding, assembling, or packaging. A simple microcontroller is more than enough to handle these jobs. It reads signals from sensors, controls the motors, and makes sure the arm follows the right movements at the right time. These tasks don't actually require massive computing power, just reliability, timing, and accuracy, which microcontrollers are great at. But when you move into more advanced robotics, like humanoid robots or machines that have to navigate complex environments, the requirements skyrocket. Now you're dealing with real-time vision, balance, motion planning, and even AI decision-making. That level of complexity goes far beyond a basic microcontroller. It usually calls for powerful 32-bit processors, GPUs, or even full-blown computers working alongside microcontrollers. So, while basic production robots can run just fine on simple MCUs, the more advanced or autonomous the robot becomes, the more processing muscle it needs. Our next example is a microwave oven. At first, it might seem like a complicated appliance, but in reality, most of its functions can be handled by a simple 8 or 16-bit microcontroller. The microcontroller reads a keypad, sets a timer, turns a magnetron on and off, controls the rotating plate, and manages safety features like the door sensor. None of these tasks require heavy computation. They're straightforward control and timing operations. That's why even a basic 8-bit chip, like an old 8051 or PIC, is more than enough to run a standard microwave reliably and efficiently. Another exciting use of microcontrollers is in drones. At their core, drones need to constantly read data from sensors like gyroscopes, accelerometers, and GPS, and then adjust the motors to keep the craft stable in the air. These are real-time control tasks, and a mid-range microcontroller is more than adequate to handle them. Chips like the STM32 series or the Atmel AVR microcontrollers are very popular choices for flight controllers because they're reliable, efficient, and provide just the right amount of processing power for stabilization and navigation. But when you step into advanced features, like streaming high-definition video, performing onboard image recognition, or autonomous navigation, the processing requirements jump dramatically. Video encoding or computer vision is far beyond what a standard MCU can handle. For those tasks, manufacturers often add more powerful companion boards or single-board computers, such as the Raspberry Pi, the NVIDIA Jetson Nano, or specialized system-on-a-chip encoder boards. These work alongside the flight microcontroller, offloading the heavy lifting for tasks like HD video streaming or AI-based object detection. For example, to stream 1080p video at 30 frames per second. That's close to 1 gigabit of data per second. That needs to be processed. A tiny 8-bit or even 32-bit microcontroller just doesn't have the bandwidth or parallel processing ability to crunch through that much information in real time. That's why industrial drones rely on more powerful SoCs, with built-in dedicated video encoders and GPUs that can handle video compression, computer vision, and AI. So, in short, the microcontroller is the brain that keeps the drone flying smoothly, but when it comes to high-end features like video and AI, you need much more powerful hardware working alongside it. Let's take CCTV cameras as another example. At first, you might think a microcontroller could handle it. After all, it's just capturing video, right? But here's the catch. Video isn't light data. Even a single 1080p stream can be hundreds of megabytes or 1 gigabits per second before compression. Microcontrollers are great at simple, real-time control tasks, but they simply don't have a horsepower to process and compress continuous high-definition video streams. That's why security cameras almost always use system-on-a-chip processors. These SoCs come with dedicated hardware for video encoding, compression, and sometimes even AI features like motion detection or facial recognition, all in real time. Now, if you're working on a DIY project, there are camera add-on boards for microcontrollers, like the STM32 camera module. These modules handle the encoding and compression of the raw video stream, offloading the heavy number crunching off from the MCU. The MCU is just there to manage the flow of data and provide control signals. Now, don't get me wrong, modern MCUs can do plenty of math, even things like fast Fourier transforms or even digital signal processing. But there's a limit. Once you push into workloads like real-time video or large-scale AI, they'll quickly run out of steam, and that's when you really need the muscle of a high-end processor, or SoC. And this would be a perfect spot to take a small detour and look at the chip-level details of microcontrollers, SoCs, and microprocessors. Early designs were incredibly modest by today's standards. Take the original 8051 microcontroller from 1980. It had only around 7,000 transistors. Even the classic PIC-16 series, which became popular in everything from toys to appliances, typically had just tens of thousands of transistors. Modern industrial versions of the 8051, still in production today, have been refined with better manufacturing. But they're still simple chips with transistor counts in the tens to low hundreds of thousands. Even high-end 32-bit microcontrollers, like ARM Cortex-M7 or PIC-32s, only pack in a few million transistors. And then we step into the world of SoCs. SoCs don't just pack a CPU and GPU. They almost always include specialized hardware blocks, custom transistor circuits designed to run specific algorithms, like video encoding, image processing, encryption, or even AI. Unlike a general-purpose CPU, which implements algorithms via software, these hardware blocks are hardwired for the job. That means they can perform the same task orders of magnitude faster and more efficiently. For example, if you ask the CPU to compress a video stream purely in software, it would eat huge amounts of power and take large number of clock cycles. But the hardware video encoder inside your smartphone's SoC can handle 1080p or even 4K video in real time, barely sipping power. And that's why your phone can record HD video smoothly or stream movies for hours, all without instantly draining the battery. It's the power of having those specialized, hardwired circuits working alongside the CPU. A general-purpose CPU might take millions of cycles to encode a video stream, but a hardware H.265 or AV1 encoder inside an SoC can do it in real time with low power because the algorithm is literally baked into the silicon. Modern SoCs can easily pack hundreds of millions to even tens of billions of transistors onto a single chip. And at the next level, we have modern microprocessors, or CPUs. Observe how a significant portion of the die is taken up by on-chip cache memory, like the large L2 caches you see here on the left-hand side, pushing transistor counts into the billions. Also note that the above processor has two independent cores, further speeding up calculations. Thus, from a few thousand transistors in the earliest microcontrollers to billions in today's chips, it's an incredible leap in complexity, powering everything from microcontrollers to data centers. And now that we've taken that little side detour, let's get back to the main video. Next, let's take a look at modular design in electronics. It's basically designing a complex system by creating or integrating independent functional blocks, modules, that can be connected or interfaced to form a final complete product. The goal here is to reduce complexity, improve maintainability, and allow reuse of tested components. Think of modular electronics like assembling a car. Instead of designing the engine, transmission, brakes, and infotainment system from scratch, take proven components and assemble them into a working car. Electronics, and computing as well, works in a similar manner. Rather than reinventing every circuit, engineers combine modules like Wi-Fi chips, DDR memory, sensor boards, signal processing chips, and display drivers to create complex devices quickly, reliably, and efficiently. This approach follows the principle of don't reinvent the wheel. Modular design lets us scale from tiny microcontrollers all the way to advanced systems without starting over each time. Next, let's take a look at mini PCs. They are a stepping stone between single-board computers and full-size desktop PCs. They pack the power of a complete computer into a compact box, giving more processing muscle and expandability than an SBC, while staying much smaller than a standard desktop system. Mini PCs may be small, but they pack serious computational power. On their own, the CPU can deliver roughly 10 to a few hundred gigaflops, enough for everyday computing and media tasks. If the CPU has an integrated GPU, performance can soar to even 2 teraflops. That means this tiny box can approach the raw computing power of a low to mid-range desktop PC, all in a compact form factor. They may, however, throttle under heavy loads. And that's when you need to step up to the next level of computational power, a full-fledged PC. And that takes us to the next stage of our journey, Microprocessor-Based PCs, where we step into the world of full-fledged desktops, the workhorses of modern computing. And here we are. All right, let's add some extra light here. It'll make everything stand out with better contrast. We are now looking at a consumer-grade desktop motherboard. This motherboard hosts a consumer-grade microprocessor. On its own, the CPU can deliver roughly 250 gigaflops, enough for most compute-heavy tasks, simulations, and gaming. Next, we have DDR memory, short for double data rate. This is the high-speed working memory of a computer, where data is stored temporarily while the CPU or GPU is actively processing it. Modern systems use DDR4 and DDR5, which move data at billions of transfers per second, giving processors the quick access they need to keep up with demanding tasks like gaming, video editing, and scientific computing. And next, the memory bus is the superhighway between the CPU and RAM. For example, a DDR4 bus can move over 25 gigabytes per second. DDR5 pushes things even higher, well beyond 70 gigabytes per second. But modern PCIe lanes are now even faster in raw bandwidth. A PCIe 4.0 bus moves about 64 gigabytes per second, and PCIe 5.0 doubles it to over 128 gigabytes per second. This is why today's GPUs and solid-state drives rely on PCIe. It gives them the data fire hose they need to keep up. Next, a graphics card, or GPU, is a specialized processor built for massive parallel computing. Originally designed to render 3D graphics, today GPUs power far more, from gaming and video editing to scientific simulations, AI, machine learning, cryptocurrency mining, to name a few. By handling thousands of calculations in parallel, modern GPUs can reach trillions of floating-point operations per second, making them one of the most powerful engines in modern computing. Next in line are the slower peripherals, like USB, SATA, and Ethernet. Now these peripherals are connected through the motherboard's chipset. The chipset acts like a traffic controller. It manages, and where applicable, buffers and prioritizes their data before passing upstream to the CPU over a fast bus, such as PCIe 4.0. For example, a keyboard key press is forwarded immediately, while network traffic can be aggregated into larger chunks. This way, the CPU remains responsive to user inputs while staying focused on heavy-duty computation. Also, most systems use hard disk drives to store data persistently. A traditional SATA hard drive relies on spinning magnetic disks with tiny read and write heads mounted on moving spindles. Because the heads must physically shift to the right track while the platters rotate underneath, access times are measured in milliseconds, an eternity in computing terms. On top of that, data transfer speeds are capped by the SATA bus, usually between 150 and 600 megabytes per second. Hard drives still deliver large storage at low cost, but their mechanical nature makes them far slower than solid-state drives. Solid-state drives, or SSDs, eliminate the moving parts of hard disks entirely. Instead of spinning platters and mechanical heads, they store data on flash memory chips, giving near-instant access with no physical delays. This slashes latency from milliseconds down to microseconds, thousands of times faster. And while SATA-based SSDs were already a big leap, modern NVMe SSDs connect directly over PCIe lanes, reaching transfer speeds in a range of 3 to 7 gigabytes per second. With their speed and reliability, SSDs have become the standard for frequently used data that demands fast access times and large data transfer rates. Next, we will step into the world of server-grade computing, processors that make even the fastest consumer desktops look modest. Unlike regular CPUs, these processors can pack dozens, even close to 100 cores, with support for hundreds of parallel threads. They also feature massive multi-level caches, L1, L2, and enormous shared L3, to keep such a huge number of cores fed with data at lightning speed. Server motherboards typically provide far more memory capacity too. This one supports 8 DDR5 slots, allowing for staggering amount of RAM and massive bandwidth. That's the kind of memory subsystem you need when running AI training, scientific simulations, databases, or other workloads where memory speed is just as critical as raw compute power. And then there's expansion. High-end server and workstation boards can host multiple GPUs. In this system, we've added 3 RTX 4090 graphics cards, each capable of delivering over 80 teraflops of compute power. Together, that's more than 240 teraflops, the kind of performance you'd associate with a small-scale supercomputer. When combined with the CPU's own multi-teraflop capability, you're looking at a workstation that can render complex 3D scenes, train large AI models, or crunch massive datasets in record time. This is where desktop computing ends and workstation and server territory begins. Systems like these form the backbone of industries, from film studios rendering entire movies to research labs simulating the laws of physics, and companies training the AI models of tomorrow. Up next, let's uncover the origins of data centers. Back in the 1990s, researchers came up with something called Beowulf clusters. The idea was simple but powerful. Instead of buying an insanely expensive supercomputer, why not take a bunch of ordinary PCs, hook them together with Ethernet, and use Linux to make them work as one? Suddenly, labs and universities could get supercomputer-like performance at a fraction of the cost. At the same time, in the enterprise world, another trend was taking shape: rack-mounted servers. These weren't about clustering at first. They were about making computing dense, standardized, and easy to maintain inside server rooms. Instead of piles of desktop machines, servers were designed to fit neatly into 19-inch racks, stacked side by side with better airflow and power management. Fast forward to today, and we can see how these paths converged. Modern supercomputers and data centers are basically the same idea as Beowulf, just supercharged. Instead of a few dozen PCs, we're talking thousands of specialized rack-mounted server nodes, linked with ultra-fast interconnects, powered by CPUs, GPUs, and even AI accelerators, and cooled with industrial-grade chiller plants. Traditional data centers mainly relied on high-end server-grade CPUs, but modern AI data centers are generally GPU-heavy, built to deliver massive parallel computing power needed for training and running today's AI models. Beowulf clusters were mostly experimental, built for research, but the principle they proved, that you could scale out by linking many smaller machines, became the foundation of modern high-performance computing and the rack-based data centers we rely on every day. In other words, the internet backend infrastructure we take for granted owes a lot to those early Beowulf pioneers. Also, data centers generate enormous heat from CPUs and GPUs running 24/7. To prevent overheating, industrial chiller plants and advanced cooling systems circulate chilled water and air, ensuring servers run reliably and efficiently. And as we wrap up this whirlwind tour of computing, remember, even the most powerful processors are nothing without storage. In the next video, we'll dive into RAID, SAN, NAS, and NVMe over fabrics, the systems that keep data safe, fast, and always accessible. And as always, thanks for joining us on this journey. Also, do check out the description section, as well as the pinned comment, for additional technical information of several topics discussed here. If you enjoyed this video or found the content informative, do give it a like. subscribe, share, and also do leave a comment. See you in our next journey.